Okay, welcome back, everybody, to the afternoon session number 9. I'd like to introduce you to John Haywood of Unium Bioscience. Going to talk about something really rather quite important, I think, which is certainly nitrogen use efficiency. It's the stumbling block of most, and certainly something that is becoming more and more to the fore with the price of nitrogen fertilizer. So without further ado, John, I'll leave you to it. If people want to ask, leave them in the Q&A, and hopefully we'll have a bit of time at the end to ask or grill you on your knowledge. Okay, over to you.
Thanks, Ben. So let's look at where plants start and where they evolve from. A quick refresher, really. They've always had plenty of light. They've always had sufficient water in general, abundant amounts of CO2. They've grown in atmospheres way more than we have now, so that's not an issue for them. Often they've had adequate growing seasons, but the major growth limiting factor has been the supply of nitrogen. But what we've seen, and you look at the rainforests and everywhere else of the forests and savannas, they've prospered in spite of this. And one of the ways that they've done that is the key evolutionary mechanism they developed is a high affinity uptake mechanism for nitrogen. Now, when you look at nitrogen, we know it's one of the most abundant mineral elements in plants. We know it can be taken up in several ways. And we know that there are several environmental factors, whether that's the soil, whether that's temperature, etc., because it's biologically mediated, that can have a very large impact on the availability of nitrogen from the soil. And what you see is there's an optimal ratio of ammonium, nitrate to ammonium around 2:1, depending on species. This can drop significantly to 4:1 under different stress conditions, particularly things like phosphorus. So when we are considering one nutrient, we have to look at others in association with it. So when you look at nutrient efficiency, there are many factors, whether this is nitrogen or nutrients in general, that can have a major implication on its availability, its assimilation, and its utilization in producing yield and also quality. They can be nutrient synergies, they can be antagonisms. For example, the classic antagonism of when you have phosphorus, high levels of phosphorus, it will limit zinc uptake. The environmental conditions we've spoken about, the form of the nutrition that we deliver, whether that's a granule, whether that's a liquid, whether that's natural as compost, the timings of those relative to the physiological stage of the crop and its ability to assimilate and utilize them. Looking at plant genetics, are there variations between different crops? And even amongst varieties, and we heard some of that with Wilfred earlier, and you'll see some examples that maybe support that. Massively is looking at the use of cover cropping. And then on top of that, to increase efficiency, is the judicious use, and I use that word carefully, of biologicals and biostimulants to maximize these efficiencies. And here's an example of looking at the interaction of P and K. With the prices of fertilizers, the availability of fertilizers, there may be a temptation to think about going on a P holiday or a K holiday, but classically you can see here when you look at the scale of P increasing as you go to the background and nitrogen increasing as you go from right to left, you can see that increase from 1 right the way up to 4.4. So we have to make phosphorus available to get the maximum efficiency from our nitrogen. So again, don't look at nutrition in isolation. Harmonization and balance are the challenge. And that's what we see within a plant. And it's called nutritional stoichiometry, looking for that balance. As you increase one nutrient, the plant will look to maintain balance and order within the levels, and therefore it will look to increase potassium or sulfur if you've got a flush of nitrogen going in to manage that influx. We know there's a challenge with efficiency, and we know we can improve that. And we're looking at the prices to think about potentially up to 50% of your nitrogen not seeing the crop that you're applying it to. That's a lot of cost. And if you average that out over NPK, it's running at around 38%. The challenge is knowing which 50% is seen by the crop and which 50% isn't, and how we can improve that efficiency. And I think that's where, through sustainability and regenerative practices, we're learning a lot more about how we can deliver these nutrients to the crop effectively. So when you look at your nitrogen uptake curve, where are you on this curve? If you're at the lower end towards the left, you need to look at your nitrogen availability, your sourcing, your supply of nitrogen. As you're getting towards that leveling off period in the middle, it's about assimilation. You've got your nitrogen into the plant, but are you assimilating it effectively and efficiently? And then as it starts to tail off towards the end, you've got your nitrogen into the crop, you've got it assimilated, but how are you going to utilize it? Can we transfer that from the biomass that we've produced in season through into the yield and also into the quality of that crop that we're looking for? So a couple of things to look at in terms of the 4 areas we'll go through here: acquisition and absorption. Really the key thing there is looking at rooting and what's going to drive your rooting to acquire the nutrients, and then looking at these activity of the roots through exudation and these high and low affinity carrier systems that take that nitrogen into the plant. So we know if you look at nitrogen use efficiency, 60% of that is driven by your roots. Very good correlation. So what we need to do early on in the season when you're starting to establish your crop, build that crop, is to maximize your rooting. So there are many things that can impede rooting, and what we have to look at is how we can remove that challenge for the crop so we maximize that root structure to access the nitrogen. Roots will tend to grow to 2 things, predominantly water and predominantly nitrogen. If they bump into phosphorus on the way, that's an added benefit, but they're the 2 that they'll grow to. So we've got to maximize that root structure to maximize that absorption. We know very high nitrate levels reduce root growth by inhibiting auxin production, as you can see here on this particular chart. So again, timing of fertilizers, choice of fertilizers will have a big impact on the rooting structure and the objectives that we're trying to achieve. When you look at different crops, you can see here the different root lengths and the different structures, the difference between particularly an autumn crop where you have a longer time period to produce that root mass compared to some of the spring crops right the way through potatoes. And again, roots occupy about 1 to 2% of the topsoil. If you take things like annual meadowgrass and no doubt probably blackgrass, they're running at 5 to 6%. So you can see why they are so efficient or more efficient at scavenging and accessing nutrient, becoming very crop competitive. If you look at where we're going on rooting impacts, and this is something that Wilfred touched on in terms of varietal and breeding, generally, and these are general statements, wheat has reduced its root growth. And as Ben asked earlier, what about root interactions with microbials? And we don't really know. There's a suggestion that it's decreased. Hybrid wheat seems to reduce root growth even further, which is in contrast to barley. Hybridity seems to increase root growth. So again, we start to have to look at different nitrogen use efficiencies, not just based on the crop here, but also whether it's conventional, whether it's hybrid, where it will be in the drilling cycles, etc., etc. So the complexities are going to increase. If you look at nitrogen efficiency, plants are efficient at absorbing nitrogen at low soil concentrations. Biology is even better, but plants are pretty good. But where that changes, plants are very inefficient when we have high levels of nitrogen in the soil. So when we're putting on our high levels of fertilizer, then you will see the efficiency decrease. And we know that elements are governed by key regulatory pathways in plants, many of which at the moment are unknown. Excuse me. But there are some that are becoming clearer and more well researched. So if you look at these high and low nitrate affinity carriers, you can see at the lower end here in the darker green area, they'll be up to 10 times more effective at taking nitrogen into the plant. But of course, that's when the nitrogen concentration in the soil and the environment is at quite a low level. As that soil level increases, you can see they turn off the high carrier pumps and they switch on the low carrier pumps, which, as we said, are 10 times less efficient. And you can see then along that scale, as that uptake decreases, you can see typical fertilizer applications can lift that up to 200 ppms, whereas the high affinity ones are operating at less than 1. So is there a way that we can maintain and switch on these high carrier pumps whilst also having a higher level of nitrogen in the soil to maximize our efficiencies? Again, other opportunities are, can we apply novel fertilizer coatings, not just to one type of fertilizer, but to several, so that we can boost the performance of any fertilizers that we are using. Once we've got the acquisition and the supply there, and that's a very overview of a big topic in itself, we've got to look at how we transport that nitrogen and how we assimilate it in the plant. And in general, plants will fix it in 2 particular ways. One is the glutamine synthetase pathway, and one is asparagine. Most plants run on a 70-30 split with glutamine the dominant one, unless you're looking at legumes where it moves to more and more of a 50-50 split. And when you look at this fixation, it's then a case of what are the roadblocks to that, so we can assimilate our nitrogen better. The less free nitrogen we have in the plant, the better, because then the plant is less attractive to pests, less attractive to pathogens, and you build a more robust, stronger cell structure. So when you look at carbon and nitrogen metabolism, they link hand in hand. And 2-oxoglutaramate is the material that is the gatekeeper molecule between carbon metabolism and nitrogen metabolism. So on a warm, sunny day, photosynthesis goes up, carbon is being produced. 2-oxoglutaramate is the molecule that is the driver, that signaling molecule that says to the root structure, hey guys, we can deal with some nitrogen now. And that will either increase root production to bring more nitrogen in from the soil, or it will take it from the store areas in the vacuoles, etc., so that you can bind the two together to produce amino acids and develop growth. Conversely, when you've put on nitrogen fertilizer and you have a flush of nitrogen going into the plant, 2-oxoglutaramate is the signaling molecule that says, hey guys, I've got plenty of nitrogen, I need to find some carbon quick. So that will upregulate photosynthesis to bring carbon in, to bind the two together as quickly as you can. So that assimilation then becomes more efficient, more effective, and has consequences that we'll see as we go through the presentation. This was all discovered by Dr. Pat Unkefer at Los Alamos National Laboratory. And Los Alamos was one of the research laboratories in the US, spent a lot of money on agriculture for spy in the sky in the Cold War over Russia, looking at US food production, making the US food self-sufficient. So this is where Pat worked for over 30 years, looking at the link between carbon and nitrogen. And this is where she came up with the development of the 2-oxo gatekeeper molecule. And some of her basic research shows here, looking at the nitrogen fixation pathways we spoke about, she'll upregulate glutamine synthetase, that assimilation of nitrogen, by anywhere 128% in the roots and 178% in the leaf. So we can improve that assimilation of the fertilizer that we've got into the plant. That improves nitrogen assimilation, it improves carbon sequestration, and that leads on to things like improved tiller initiation, improved leaf protein and assimilation into that leaf structure, that then builds that biomass. That is the next step, which is the utilization of that for yield and quality. So when we look at utilization, and this pathway has only been researched approximately for the last 20 years, so you can see how new some of these pathways and signaling molecules are that we're working with. The trehalose pathway came to prevalence in about 2016. A lot of research was published looking at the area and development of this, of how we can then utilize those sugars, how we can utilize those proteins within the plant and drive it through into yield. And so here we looked at, when you look at some of the T6P materials of the trehalose 6 phosphate materials, you can see here moving into the grain and a consistent increase of nutrient density into that grain. And one of the things we've seen going back to the presentation just before looking at seed quality is this improved nutrient density improves the quality of your seed crop, which means you get better establishment in the subsequent crop. And again, looking at how we use the judicious use of biostimulants here, you can see that on average, you can move that grain nitrogen on here on average across 8 trials by 3%. So again, judicious use, looking at the right material at the right time, you can manipulate that grain quality as well. So what are the consequences of getting it right? Nitrogen, increased nutrient use efficiency is an increase in cost effectiveness. We can improve crop health using an appropriate fungicide strategy. We can reduce lodging risk with managing any PGR strategy that we're following. We'll improve nutrient soil health, and we reduce the environmental risk of any pollutions that maybe as a consequence. And if you look at the cropping here, you can see from left to right the nutrient use efficiency for nitrogen. Sugar beet being the most efficient, vining peas being the least efficient, ironically enough. But there you can see that there is a split amongst the crop, but of the main arable crops, certainly in the cereals, etc., it's a pretty even split amongst them. If you look at that in terms of wheat varieties, and this is something that Wilfred touched on with his differences in rooting structures, you can see there are variations of anywhere from 10 to 20%, depending on the nitrogen that's applied. You can see that variation across those varieties. It would have been wonderful to have an updated list of the varieties and where they sit on this chart, but maybe that's something for future research to rekindle and bring back to life, because I think it's an interesting area looking at modern varieties or older varieties. So when you look at that pathway of the glutamine synthetase, which is the predominant one we look at, we can increase nitrate reductase by using things like the phosphites. Calcium phosphite here will improve that movement from NO3 to NO2. We can deliver with biology the ammonium into the plant, particularly using things like endophytes, which are biology that live within the plant and so therefore less affected by environmental pressures. And then as you start to get into that cycling for the production of amino acids, the 2-oxoglutamate that we spoke about there, you can improve that and increase that signaling molecule and upregulate it so that you improve that nitrogen assimilation, you improve that carbon sequestration, and improve growth and development by producing more amino acids and proteins as we move along. When you start to combine all these different things, and this is some work from Nottingham University, whether it's with a fertilizer coating, applying biology, a combination of the two, and then assimilation, and then applying a full program here, you can see that you can move that nitrogen use efficiency by up to 25%. So if we know that 50% is not seeing the crop and we can improve it by 25%, then there's a big gap that we utilize that in terms of cost saving and efficiencies of our nitrogen fertilizer. So what does that mean when you put it in the field? Well, here you can see using a biological material called Tyros, you lift the yield by 0.37. When you apply 2-oxo on its own, which is in the assimilatory step, that improves it by 0.81. So that would tend to suggest in this particular case, you might be looking at more assimilation than supply. But then when you combine the two, you can start to see 1 + 1 = 3. And I think when we look at any of these products, when you look at any of the solutions that are offered, when it comes to nutrition, there's no silver bullet. It's looking at a program, could be products from wherever, that combine together to evolve and develop this system that will increase your efficiencies. Oh, sorry about that. So when you look at nutritional health in general, here you can see all the different elements. When you look at all the peer reviewable papers, from 1,200 that have been cited here, when you look at nitrogen, it's one of the major impacts is to increase disease, not to decrease it. It's kind of sat in the balance, but 60% is in favor of increasing it, whereas most other elements are in favor of decreasing it. And here you can see a picture looking at when you manage that nitrogen right, and when you have less free nitrogen there to attract and support pathogens, and when you also apply things like potassium to that crop, you can see you get less impact from things like septoria. When you push out those roots, having no impact on the disease itself, you just got more roots there to withstand any and mitigate any attack from, in this situation, take-all. You can see that you can have a fairly significant impact on that particular problem. So again, it's not working as a pesticide would, it's working by manipulating the impact that the pathogen has on the plant. Equally, we know that you manage your nitrogen better if you allow that crop to grow in balance. As we talked about the stoichiometry, it will bring in calcium at the right rate to manage that growth and maintain that cell wall structure. And here you can see when you can do that with a range of technologies, you can see you can lower your lodging risk. We left UBS 004 in there because it didn't do any of that, and it was exactly the same as the untreated. So not every product will deliver all these benefits. So in summary, you've got to maximize your nutrient synergies between the different nutrients. Don't just look at them in isolation. Minimize any limitations. And again, good soil testing, good soil management, sap analysis, tissue testing, etc. through the season in detail in a key area of the farm to allow you that management opportunities is a really great idea. Look at your nutrient form and technology that you're applying through the crop, relate that back to your soil types, etc., and the levels that you've got. Look at the timing of those applications relative to the physiological stage of the crop, and what else you can do at that time to make sure it's either taken in better or assimilated quicker, etc. Look at plant genetics, and I think that's where I would encourage the breeders to look at that, to say, okay, which varieties we can manipulate our programs more with. Cover cropping and the use of biologicals, biostimulants are critical to get that balance correct. So to summarize, get to know your soil well. This isn't one of you looking down one of your soils, Ben, but what I'd always do, please remember to fill the hole in after you've finished sampling. So that was a quick whistle-stop tour, picking on a couple of key ideas. Thank you very much. You'll find us on all the usual platforms, and if there's any questions outside of today, please feel free to get in touch, and we'd love to hear from you.
Awesome. Thank you very much. That was enlightening as ever. An awful lot of information in that. Thankfully, these presentations are going to be available, I think, from Monday for everybody that's subscribed, so they'll be able to pick the bones out of that. We've just got enough time for a question or two, so I'm going to kick off with one. I guess as a regenerative farmer consultant, there's a whole industry rapidly growing on the fact that the magic potions and snake oils of improving soil health, plant health, all of those sort of things is gathering some incredible pace and almost falling into the same trap as where we left.
Yeah.
How do we decide? You know, in what I'd almost say is a totally unregulated industry right now as well. So how do we really avoid the snake oils and all the problems, and actually choose the correct products that have actually got research behind them and not just done on a one trial found somewhere and that sort of thing? So that would be my biggest question.
I think that's a really great question, and I think one is regulation is coming. EU are starting with that, and potentially the UK could follow in the same standards. It's not very onerous. Will it clear out the products that you're talking about? Probably not. And I think equally, if there are snake oil products in the market, sometimes we have to take our own responsibility because they exist because we buy them. Now the challenge is, as you've put, is how do we identify them? And in the work we've done, if you look at picking the right product at the right time in the right situation compared to just putting a more generalized product through all the time at the same timing through the crop, we found the difference to be over 1/4 of a ton. So there is the case that, you know, one product doesn't fit all, one shoe is not going to be the answer. So you've got to look at for those which are the right products at the right time and why. And I think when you then go back, you say, well, look, is this product peer reviewed? Is there academic, like we saw in the previous presentation, you know, research and data behind it that shows the proof of principle? When you've got that proof of principle, okay, has it then been done in small plot trials and evaluated properly that you can show me that data? And then critically on top of that, I think you also need farm experience, because like with biological products, there's a gazillion products that work in a laboratory that fix nitrogen or solubilize phosphorus or whatever they do. But there's also a gazillion that don't work when they're practically applied to a soil for many different reasons. So I think, you know, it pays to do, as whether that's as a farmer or an agronomist, your homework. Look for the products and look at the information that you get with them, and look at that detail and really scrutinize it. And then I think, as you'll know from training and reading, that, you know, when you're looking at fermentation of biologicals, it's an incredible difficult challenge. Have you got the air oxygenation right, et cetera, et cetera? So, you know, I think it goes back to quality, and you then try the product, look at the product, see if it fits into your system of what you're trying to do. I think the key thing is decide what the objective is of why you're putting something on. And if you know what the objective is, you can then measure it. But if you don't know why you're doing it and doing it, well, I'm relieving stress, or, you know, I'm just doing it because it feels good, or I've been told to do it, it's difficult to measure. And I think anything that relies totally on stress, we build stress mitigation as part of the product, is difficult because you can't measure the stress a crop's under. It's very difficult. So then you can't manage it. And so, you know, big claims on measuring stress, and, you know, you suddenly get 40 degrees and, oh, you need to do this. Well, the stress might be bigger than any product you're going to put on. And if you haven't got the data to say yes or no, then it becomes very difficult. So I go back to data. It's data, data.
I think you're absolutely right. I think there should be a due process of bringing these products to market, and like you say, need to be peer reviewed, need to be taken right the way through an almost trial program, not dissimilar to AgChem. So I totally agree. Typically, I run over time because I haven't actually managed to keep the session on time today. So I thank you again, John, for a fascinating presentation. It was brilliant, and yeah, we're going to move on to the next afternoon session. So thanks very much, John, and
pleasure. Thank you very much.
I'm sure I'll catch up with you again soon.
Alrighty. Thanks, Ben. Thanks, everybody. Bye.